Okay, let's talk about fraction fields. We encounter this idea very early in life when we construct the rational numbers from the integers. So what's a field? You all probably know this. A field is a ring where every non-zero element has a multiplicative inverse. And the first example of a ring that we encounter in life is probably the ring of integers z. And the first example of a field that we encounter is the field of rational numbers. And in school we are told that a rational number has elements of the form p over q, where p, q are integers and q is not equal to 0. But you cannot think of rational numbers as just pairs of integers. You can have the same fraction given by two different pairs of integers. So you have this relation that p by q is equal to r by s if and only if ps is equal to qr. So this passage from integers to rational numbers, it's not it's fairly intuitively obvious, but there are several things to be checked. But the nice thing is that this passage from integers to rational numbers works in a much more general setting, namely when you replace the integers by any integral domain. So let's go through this process step by step. So let's start with R, any integral domain. And that means a commutative integral domain. And the first step in the construction of its field of fractions is to look at pairs in R. So we'll define f tilde to be the set of all pairs p comma q, where p and q are in R, and we assume that q is not equal to 0. Okay, then let's define the equivalence relation. So we'll say that pq is equivalent to rs if ps is equal to qr. Now it's not enough to say that this is an equivalence relation. We need to check that this is an equivalence relation. So this relation is it reflexive? So that's very easy. We want to know if pq is related to pq. But what does this condition mean? So this is just because this condition then becomes pq is equal to pq. This when we put r equals p and s equals q, then ps equals qr becomes pq equals pq. And I claim that this is also symmetric because if pq is related to rs, then this is the same as saying that pr is not pr, ps is equal to qr, but that's the same as saying that rq is equal to sp. That's because we are in a commutative ring. But this is the same as saying that r comma s is related to p comma q. Transitivity is a little more involved, but it's not very difficult. Let's see. So if pq is related to rs and rs is related to, let's say, tu, then this means that ps is qr and also ru is equal to st. Okay, now let's multiply these two equations together. So what we get is psru is equal to qrst. Now both these factors have rs, so let's take it out. We're in a commutative ring, so we can move these things around. So we get rs times pu minus qt is equal to 0. Okay, now S we already know it's not 0. So if R is not 0, then RS is also not 0 because we are in integral domain. PU minus, so that means PU minus QT is 0 because again we are in integral domain, which implies that U PQ is equivalent to TU. On the other hand, if R is equal to 0, then we already have that QR is PS, but we know that Q is not 0. That means PS is 0, but S is not 0. So then that implies that P equals 0. Also, if R is 0, then RU is 0, which means that ST is equal to 0. But we know that S is not equal to 0, which implies that T is 0. But then that also means that PU is 0, which is equal to QT. So PQ is equivalent to TU. So this relation is an equivalence relation. And whenever you have an equivalence relation, you can talk about equivalence classes. So what we've said is that this is an equivalence relation and so you define F to be the set of equivalence classes in F tilde. With respect to this relation tilde. And now this is going to be the field of fractions. So on this we will define, firstly we'll define addition and multiplication on F. So you have define P comma Q plus R comma S to be so you do it as if these are just fractions. So what you'll get is the denominator you'll get QS, and in the numerator you'll get PS plus RQ. This is just the rule for adding fractions, right? We would take P over Q plus R over S, then we would take the common denominator QS and we'll get PS plus RQ. Okay, and what you need to check is that this descends. So this is a priori, this is defined on F tilde. So it's a binary operation on F tilde cross F tilde, and it's giving you another element of F tilde. But what you can check is that if you modify PQ by something that's equivalent to it, you replace PQ by something that's equivalent to it, and you replace RS by something that's equivalent to it, then this expression PS plus RQ comma QS will also get replaced by something that it is equivalent to it. A binary operation F cross F to F. So you need to check this. It's a bit tedious, but it's not difficult. And then you can also define multiplication the same way. Define P comma Q dot R comma S to be PR comma QS. And this again is just, this, if you're multiplying fractions, then you just multiply the numerator and you you multiply the denominators. And this descends to a binary operation F cross F to F. So what we have is the set F, which is a bunch of equivalence classes on F tilde. This gets two operations, addition and multiplication. And then you can check that with these definitions, F plus dot forms a ring. So you need to check all the ring axioms, and again it's many things need to be checked, but none of them are really difficult. Forms a commutative ring, in fact. Okay, and we'll use the notation P over Q denotes the equivalence class of P comma Q, which is an element of F tilde in F. So the equivalence class of P tilde Q, an element, this equivalence class is an element of F. So in this, with this notation, we literally have that P by Q is equal to R by S if and only if PS is equal to QR, because in that case these equivalence classes are equal, they are the same equivalence class. Okay, so let's just point out some features of this ring. So what is the zero element? So 0 by 1, which is the equivalence class of 0 comma 1. What is the equivalence class of 0 comma 1? So let's see, 0 comma 1 is equivalent to P comma Q if and only if 0 into Q, which is 0, is equal to P into 1. So this is consists of all elements of the form 0 comma Q, Q not equal to 0. This is the equivalence class of 0, 1, and this is denoted by 0 divided by 1. So this is the additive identity of, is the zero element of R, is the zero element of F. It's the additive identity element of F. And 1 by 1, so this is equivalence class of 1 comma 1, which turns out to be the same as Q comma Q, Q not equal to 0, is the multiplicative unit of F. And so if you have a class that is not 0 in F, well, what does that mean? That means it's not equivalent to 0 by 1, which means that P is not equal to 0. Then you can form the class Q by P. So that's another equivalence class in F. Because we have P not equal to 0, it makes sense to talk of Q by P. And what we get is P by Q into Q by P is PQ by PQ, which is in the equivalence class of 1. So I'll call this now 1 and this 0 in F. So what we've seen now is that every non-zero element of F has a multiplicative inverse. So the conclusion is that F is a field. What's more, R itself sits inside F. So given R in R, define iota of R to be the fraction R divided by 1. Okay, and it turns out that this iota is a function from R to F. It turns out that this is an injective function. That's not difficult to see, because if R by 1 is equal to S by 1, that the definition of equivalence implies that R is equal to S. So let me just summarize what we've done so far in terms of a theorem. So F is a field. So maybe the first assertion. The second assertion is the map iota from R to F defined by iota of R is equal to R over 1 is an injective ring homomorphism. So basically what this is saying is that R is sitting inside F as a subring. And there's a third property which is worth noting, is that for each x in F, so if you take any element in F, then you can multiply it by some element of R. There exists Q in R such that Qx is equal to iota p for some p in R. So this is like the property that if you have any rational number, you can multiply it by some integer to make it an integer. So it means that so if you start with integers, you don't want to end up with real numbers or complex numbers. You want to just add just enough elements so that you get the rational numbers. And this last property is what characterizes the rational numbers. If you take any larger field containing rational numbers, then it will not have this property. So these three properties characterize the field of fractions of an integral domain R. So the prototypical example of field of fractions of an integral domain is the construction of the field of rational numbers from the ring of integers. But let's look at some more examples. So the first example that we look at is when we take for the integral domain kx. So this, as you recall, is the ring of polynomials in one variable x with coefficients in k. This k itself is a field. And then the field of fractions is called is usually denoted k round brackets x, and it's called the field of rational functions. And a typical element of kx is px by qx, and where px and qx are polynomials and qx is not equal to 0. Of course, this represents an equivalence class of pairs. So there could be other pairs p comma q which represent the same rational function. These things can actually be thought of as functions. Well, they're not defined everywhere. So if S is the set of roots of Q, i.e. it's the set of x in K such that Qx is equal to 0. Then let's call this f of x. Then you can define a function from k minus x, k minus s to k. You can think of this rational function as a function from k minus s to k, which takes an element x to p of x by q of x. So for example, you can think of the function 1 plus x by 1 minus x. This is a rational function and it's defined at all values of x in the field except for x equals 1. Okay, so this is one very useful example of a field that comes from this construction. Let's look at a second example. In this case, we'll take R to be the ring of Gaussian integers. Remember, these are just integers of the form, not integers of the form, complex numbers of the form a plus bi, where a and b are integers. And we had seen that this is in fact a Euclidean domain. So now, what is a typical element of the field of fractions? So if f is the field of fractions, then a typical element is of the form we can write it as a plus bi over c plus di, where we assume that either c or d is non-zero. Okay, but there's another way of describing this field of fractions. I'll define qi, very analogous to zi. It's the set of complex numbers of form a plus bi whose real and imaginary parts are rational. And now I'll define a function phi from f to qi as follows. So I'll take this thing a plus bi over c plus di and map it to, so I need to map it to something of the form a rational number plus I times another rational number. And so what I'll do is, well, it's sort of motivated by trying to express this fraction as a complex number, which will turn out to have rational, real and imaginary parts. So remember that a plus bi times c plus di is the same as a plus bi times c minus di divided by c squared plus d squared. This is how we divide complex numbers, right? So we can write this as, map this to a plus bi by c squared plus d squared. No, what do I want? I want the real part, so that's ac plus bd by c squared plus d squared plus bc minus ad over c squared plus d squared times I. And this is an isomorphism of rings. So that's easy to check. You can check that this gives rise to an isomorphism of the ring F with the ring Qi. So these are actually isomorphic fields.